Okay, welcome back. I'm going to show you our answer for problem 4 in self-study exercises number 11. We are given with a reduction of iron oxide by aluminium metal. Okay, this reaction is known as thermit reaction, and it's a very important process that produces molten iron metal in situ. Okay, right. The first thing is to balance the equation for the reaction. I think it should be very straightforward. So we are given with iron Fe2O3 oxide reacting with aluminium. Okay. Producing what? Aluminium dioxide, aluminium 2O3, and pure iron, which is molten. Okay, and iron. Now I have to balance these two aluminiums and these two irons over here. Okay, we can think about this reaction as redox, and if you remember, one of the classifications of redox is the gain and loss of gain of oxygen. So in this particular case, we can see clearly that aluminium has gained oxygen, forming aluminium dioxide, whereas iron lost its oxygen, forming pure iron. Okay, and remember that gain of oxygen is oxidation, loss of oxygen is reduction. Okay, right. So what's next? An iron ore, okay, was first found to contain 59% by weight of iron oxide. Okay, so it's not very pure iron ore, to be honest. And then heated with 1.71 kilograms of aluminium. Okay, which substance? So it's under high temperature. Okay, which substance was the limiting reagent? Show us your calculations. So in order to understand which reagent is limiting, we first have to calculate the number of moles of each and then decide from the reaction stoichiometry which number is the smallest, and that number would be the number of moles of the limiting agent. Okay, or reagent. So first of all, let us get the mass of iron, because it's only 59%, okay, in 9.7 kilograms. Okay, that will give me 5.72 kilograms of iron in the iron oxide, in the ore. Next, the number of moles of iron then would be what? Mass over molar mass, or in this particular atomic mass. 5.72 kilos, okay, over 56 times 2 plus 16 times 3, okay, and because we're taking this as grams per mole, I have to convert this into grams. Okay, therefore I will multiply to 1,000. Okay, the answer for that would be 35.75 moles of iron. Now next, find the number of moles of aluminium. Okay, it will be the same approach, 1.71 kilograms times 10 to the power of 3 grams over atomic mass, or atomic relative mass is 27 grams per mole. That will give me 63.33 moles of aluminium. Okay, now I have to look at the reaction stoichiometry and decide. So I have 1 mole of iron oxide and 2 moles of aluminium. So I would have to divide each number of moles per its stoichiometric coefficient. Okay, and I can conclude that this number is smaller than this number, therefore aluminium is the limiting. Okay, which means that the iron oxide Fe2O3 is in excess. Okay, now that I know that aluminium is the limiting reagent, it's asking me calculate the theoretical yield of molten iron produced. Okay, molten iron produced, which is this one, knowing the number of moles of aluminium, which is this one, I can see that from stoichiometry we see that the ratio between both of them is 1 to 1. Okay, so to calculate the mass of molten iron, I would use the number of moles of the limiting agent, which is aluminium, and it will be actually equal. The number of moles of iron would be equal to number of moles of aluminium, and it will be equal to 63.33 moles. Okay, in order to get the mass, I need to multiply 63.33 moles over times 56 grams per mole. That's the atomic molar weight of iron. That'll give me 3,546.5 grams, or 3.55 kilograms of pure iron from the reaction. Okay, from having the 9.7 kilograms of iron ore, where we have 59% by weight of iron oxide. Okay, thank you for watching. That's the end of the video solutions for self-study exercise number 11, which is on redox.